So this is it, folks. This is the last chapter, the last unit of BC Calculus. We're almost there, and this is the granddaddy of them all. This is Taylor Polynomials. This is the part that we've been building up to all year long. As we've already talked about in class, we know that Taylor polynomials are polynomials that are used to approximate transcendental functions such as sine of x, e to the x, natural log of x, non-polynomial functions. So we're going to start with a problem that should seem very familiar to everyone. We're going to find the tangent line for sine of x at x equals 0. So one way we can do this is we can start off with our function sine of x, and we can take its derivative and get cosine of x. And the reason we care about its derivative is because it's going to give us the slope of the tangent line. But the reason we care about the function itself is because we need the y value as well. And of course, both of these change depending on what value of x we pick. So we're going to pick a particular value of x, the value of x they tell us to pick, which is x equals 0. So we're going to find the y value of that point of tangency. It's going to be 0. We're going to find the slope of the tangent line at that point of tangency. Cosine of 0 equals 1. And that now we have a point and a slope, and we can create the equation for the tangent line. Now I'm going to call this p sub 1 for polynomial of degree 1. It's a tangent line, so of course it's linear, degree 1. And we're going to write this out as f of 0 plus f prime of 0 times x. Okay, this is perhaps a format that we haven't used a whole lot in the past, but it's going to help us in this unit. So p1 of x is a function of x, and we know that f of 0 equals 0, and we know that f prime of 0 equals 1, and so we've got p prime of x equals x. That's the equation of the tangent line of the sine of x at x equals 0. So remember that the tangent line is a local linear approximation, squiggly equal sign, of the function. So we know that x is approximately equal to sine of x for values of x close to 0. Why 0? Because that's the point of tangency. So when we say local, we're talking about close, local linear, or close to the point of tangency. So that's why we can use the tangent line to approximate the function. So we know that the sine of 0.2 is approximately equal to p1 of 0.2. Well, that means that the sine of 0.2 is approximately equal to, well, I'm just going to replace this x with 0.2. I'm going to get 0.2. Oh, well, that's interesting enough. All right, so how do we determine whether this is an overestimate or an underestimate? Well, think about the graph. We know what the sine of x looks like. If we graph the sine of x looks like this. It kind of goes through the origin, kind of wiggles around, and at the point x equals 0, y equals 0, and the slope of that tangent line is 1, and we have ourselves that, that p1 of x is the orange, and the green is f of x, or y equals the sine of x. And we know that for small values of x, like for x equals 0.2, the two are close to each other. But as we look at this graph, we can see that it is concave down. The green is concave down from x equals 0 to, for a while, until I guess we get to x equals pi. Way after we hit x equals 0.2. So because this is concave down over that entire interval, we know that our function is curving down away from the tangent line, while our tangent line is consistently heading up at a constant slope. After all, that's what lines do. Therefore, we can conclude, because of the concavity of the graph, that the sine of 0.2 is actually less than 0.2, or our approximation is an overestimate. But it's perhaps a decent approximation. All right, so we've been doing this all along. We didn't know it until now, but we've been dealing with Taylor polynomials when we find tangent lines. We're just dealing with degree 1 Taylor polynomials. But we can actually take this to higher degrees. Remember, what we're talking about here is polynomials of high degree, not just degree 1 like a line, but degree 2 or 3 or 4, or hey, let's go all the way up to 7. and get a degree 7 polynomial that approximates our function. So we've already talked about this a bit, but if you don't already know, we know that the 7th degree Taylor polynomial for sine of x centered at c equals 0 or x equals 0 is sine of x is approximately equal to x minus x to the 3rd over 3 factorial plus x to the 5th over 5 factorial plus, or minus rather, x to the 7th over 7 factorial. Now, it says that you should graph these on a calculator. I'm not going to worry about graphing this because I know you guys know how to graph things in Desmos. I've mentioned that about 5,000 times this year. So I encourage you guys to do that and take a look at what that graph looks like. And then fill out the chart. So what chart am I talking about? What they're asking you to do here is compare P1 of x, which is equal to x, to P3 of x, which is equal to x minus x cubed over 3 factorial. Compare that to P5 of x, and compare that to P7 of x. And then also, finally, to compare that to the actual function that we're approximating, which is sine of x. And what are we comparing? We're comparing these values when x equals 0 and when x equals 0.2. And try to make some predictions as to what's going to happen before you actually do this, and then go ahead and fill out the chart and see if your prediction holds.